तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
In the last lecture we talked about the basic gates, and we also said the AND or invert combination can implement all logic functions. In addition to this AND or invert, we also saw a few more gates like NAND, NOR, exclusive OR and exclusive NOR or equivalence. I also mentioned in the last lecture that even though all functions can be implemented using AND or invert, practically any digital system can be implemented using AND or invert. Sometimes for reasons of practicality or the type of design is, or because that is the inventory available, or because of the technology reasons, we go in for other types of gates like NAND and NOR. And NAND and NOR have a special place in the sense they are called universal gates. I already mentioned this to you. That means you can implement a whole logic. Whatever you can implement using AND or invert combination can be implemented using NAND gates alone. Similarly, NOR gates alone. So NAND and NOR for this reason are called universal gates. So I will quickly tell you how to why this is so. Why is an AND gate or an NOR gate universal gate? So let us look at a NAND combination. If you assume my premise that any logic function can be implemented using AND or invert, that we will see later on more elaborately. I don't want to prove that to you now. You will have to take my word for it at this point. So if you assume that, then all I have to show you is how do you use a NAND gate to get an AND gate, NOR gate and a NOR gate. That means if you are going to believe me when I say you can get any logic function, any digital system implementing to be implemented using AND or invert, and if I prove that NAND can be used for each one of them, then you know that NAND is a universal gate. Is that right? That is the way I am going to prove, because I don't want to be spending a lot of time on this. So we know how to get a AND out of NAND, because NAND with an invert is an AND. So first let us see how to get an invert using NAND. What is an inverter, if you remember from last lecture? F is equal to A bar. Now let us have a NAND gate with both the inputs tied together, and call this A and F. Now, in the NAND gate, if you remember the NAND gate truth table, you remember I call this truth table. Is this NAND gate? Is that right? Now, I am making A and B are same. So, that means A is 0, B can be 0 or 1 because there is only one of them, F is 1, and let us say now A is 1, oh wait a minute, what? Both, that means these are the only two combinations possible, right? A and B both 0 0, A and B both 1 1. So if both are 0 0, output is 1. That means if A is 0, output is 1. If both are 1, the output is 0. Correct? So a NAND gate with both inputs tied together is an inverter. Is it okay? So that means I don't even need this. And A is 0, B is 1, and this row is also not there. So A is 0, output is 1, A is 1, output is 0. This is this combination. So NAND as an inverter. Any questions here? All you have to do to get an inverter after NAND is to tie the two gates together and apply the input variable. The output is the complement of the input. And once you know the NAND can be used as an inverter, NAND can be used as an AND gate because NAND is nothing but AND invert. So if you invert it one more time, this is A, B, NAND. So this is NAND invert of this A and B, which is this is an invert. This bar will be removed. This bar is because it's a NAND. This bubble, I told you the bubble is the key thing. The bubble is the key thing. Bubble inverts and bubble also removes the inversion. One bubble inverts, the next bubble removes the inversion. So you have the bubble here with a invert, and remove this invert removes this bubble removes this invert sign. So this is a AND gate. So I can get an AND from a NAND by putting a NAND in series with an inverter. An inverter itself can be gotten out of NAND by tying both the inputs together and applying the input. Then third thing is of course the OR gate. How do you get an OR out of NAND? So let us take a NAND gate with two inputs A and B, invert them each. I tie an inverter to each one of the inputs of the NAND gate and apply my variables A and B instead of to the NAND inputs to the inverter inputs. So that means this is here A prime or A bar, here this is B bar, because there is a theorem called De Morgan's theorem. You might have heard of that, we will see it later. Without going to that now, since I did not introduce it, I can write a simple truth table A, B and F. If A is 0 and B is 0, this is 1, this is 1. So when you have 1 1 to the NAND gate, output is a 0, 0 1. When you put a is equal to 0 and B is equal to 1, this becomes 1 and this becomes 0. When I put a 1 0, 1, 1 0, put A is equal to 1, B is equal to 0, this is A bar is 0, this is 1, 0 1, input, output is 1, 1 1. When you give A is equal to 1 and B is equal to 1, this becomes 0 0. When I get 0 0 to the NAND gate, the output is a 1. That means this is the property of a OR gate. So this is an OR gate property. So I get a property of OR gate by taking a NAND gate and inverting each input. I get a property of AND gate by taking a NAND gate and putting an inverter at the output. And I get the inverter itself by taking a NAND gate and tying both inputs together. So to summarize here then, an NAND with two inputs tied together is an inverter. A NAND with inputs, if you want to put it in the NAND way, this is what? A or B? This is A and B. Is that right? So that means I can use a NAND gate to get an inverter. I can use a NAND gate to get an AND gate. I can use a NAND. I have not used A. I can use NAND gates to get a AND gate. I can use NAND gates to get OR gate. I can use a NAND gate to get an inverter. Because of that, NAND gate can replace every gate in an AND or invert combination. And as I said, if you accept my premise in the beginning, which I made in the beginning, that any digital function, even sequential, we'll see later, any digital function, any digital system can be implemented using AND or invert. A NAND gate can alone do the job. That is why NAND is a universal gate. NAND is a universal gate. Now then, I can use only NAND gates. This is technologically easy. Think of this as a process by which I have to implement a given function or a given circuit of different complexities of a specific complexity, where there should be some AND gates, some OR gates, some NAND gates. We are not aware of at this stage circuit requirements or the technological requirement, process requirements as of now. But surely it will be nice to have only uniform type of things to be done, either circuit wise or technology wise, either for making something or designing something. If everything is identical, is it not easier? Can you sort of intuitively visualize that an all NAND solution may be a little simpler to do than a AND or invert solution? From point of view of circuit design, maybe we don't know at this stage whether it is going to use more NAND gates or less NAND gates compared to the original number of gates. The number of gates we don't know at this point in time. It looks like we have to put more gates because we have to put two inverts for an OR gate, one invert for the out gate, AND gate and all that. But later on we will show you techniques by which it is not all that extra gates. There may be some extra gates, but there will be some knocking off. There may be an invert. For example, I may have an invert at the output of a function and an invert at the input of the next function. I can cancel those two inverts. So two inverts I can save by, because one invert, again another invert, I can save them. So maybe some effective design technology can be used, design techniques can be used to improve the density. Let us not worry about that. In principle though, it is better to make a circuit more from a designer's point of view, more than from a designer's point of view, from a technology point of view. From the point of view of making these ICs, it's a complicated procedure, it's a complex procedure. It is nice to have identical things to do. So from that point of view, people prefer this type of implementations. So that's why I said, even though all are called basic gates, AND or invert, NAND, NOR, exclusive OR, exclusive NOR, these three are fundamental gates, AND or invert, because these are required to implement logically, mathematically, in a mathematical sense or a logical sense. AND or invert are required to implement any given digital function or digital circuit, digital system. But it also be equally well done using NAND or NOR. That is why NAND and NOR are universal gates. Now I am going to give you an exercise. I am not going to do the same thing for NOR. Do the same thing for NOR. Exercise. Show that NOR is a universal gate. Very simple. Same way you did this. You start with inverter and OR gate and NAND gate. How to get each one of them using a NOR gate or using NOR gates. Then in that case I have now a variety. I have a choice of making a design. When I want to build a circuit, I have a choice of using this or that or combination thereof or whatever. That gives me more flexibility in terms of design, in terms of the technology I can choose and things like that. So we have introduced you to the concept of digital systems, a digital signal and two levels, binary, and how binary alone cannot do the job because we cannot capture all the variations of a signal by using only two levels. So we have multiple signals or multiple bits or multi-bit signals or which can capture the variation, nuances of the variations, fineness of the variation. And then we said the thing is to build all these functional blocks which can do all the things we need to do, and we said there are two types of circuits, combinational and sequential, and we said we will start with the combinational, and for the combinational the basic building blocks are the gates, so we introduce the gates. So at this point in time what we will do is we will use these gates to implement a few circuits. How to get a circuit using gates for a given specs, that is the design, or how, given a circuit, how do you analyze to get the function. So let us start with that. Let us take a simple example of a combinational circuit. Since I said most circuits are implemented using and all circuits in principle, in theory, all circuits can be implemented using AND or invert. I have taken a simple circuit in which AND and OR and an invert are all used. Let us call this signal A, B and C, three variables. So I have a digital system or a circuit or subsystem. Don't get confused too much about this definition of whether it's a circuit or a system. What is called a circuit, what is called a subsystem, what is called a system, it's all a sort of a definition level. Anything that we want to do, we do. If it is small, we will call it circuit. If it is slightly more complex and involved, we call it subsystem. If it's huge, we call it system. Like a microprocessor, we call it a nobody will say microprocessor circuit, even though it's a circuit. Components are connected and behaves the way we design, so it's a circuit. If that is the definition of a circuit. But at the same time, it's a microprocessor too huge a thing, so you call it a system. You would like to call it a system, computer system. And a smaller thing we will call subsystem, adder, subtractor, multiplier, arithmetic functions of a microprocessor we call them arithmetic subsystem, arithmetic subunit, arithmetic submodule. And it's a simple gate structure like this. I would like to call it a circuit because a couple of gates. So I don't think you should worry too much about the definition or the use of the word. In fact, I use them interchangeably all the time. Circuit or a subsystem. I won't unnecessarily use subsystem and all that. When you are talking about system and we break it down into different modules and try to implement each one of them separately, at that time only I will use subsystem. But sometimes system and circuit I will sort of interchangeably use. Don't get too much agitated over this. Okay? So this digital circuit has three inputs, A, B and C, and one output F. Since all of us know the functions of the gates now, this is B, this is C bar, right? So this is B and C bar, I'm sorry, B and C bar, and this is A, R, B and C bar. That is the behavior of the circuit. So the functional description of the circuit is F is equal to A, R, B and C bar. But you want to be very, what shall I say, very correct about it. Say A, R, B and not C. Let us say that. A, R, B and not C. F is equal to A, R, B and not C. Anyway, this is the functional description, this is the circuit description, and then the third one is the truth table. Truth table, right? The truth table is operation, of course, involves AND operation, an OR operation, NOT operation. The first, when I introduced the gates, first I said an operation is defined by a gate, a symbol is defined by a gate, for a gate, a functional description of the gate is given, and a truth table is given. In this case, the operations are here. This is the symbolic representation of the circuit representation. This is the functional representation. So the last thing is the truth table, where I'll have A, B, C as the inputs, and C as the output, A and F as the output. So we will quickly write all the possibilities of the inputs How do you know all the possibilities? There are 3 input variables. There can be 8 variations possible, because each input can be either 0 or a 1, or true or false. Symbolically is at 0 or 1. So each of the inputs can be 0 or 1. There are 3 inputs, so there can be combinations of each one can be true or false. So there are 8 different combinations. How do you know that 8? It is 2 power 3. The number of combinations is 2 power the number of input variables. So it is 2 power n number of combinations, input combinations is 2 power number of input variables. This also is the same as the number of rows in the table. Row 0, 0, 0, 0, 0, 1, 0, etc. etc. So 8 rows in the truth table, because there are 8 combinations, and each of these combinations, what is the output, you should see. Because you know the operations, you can quickly do that. When A is equal to 0, B is equal to 0, this is 0. One moment this is 0, this is 0, this is 0, so the output is a 0. Okay? So this is 0 again, this is 0 again, this has to be 0. So if you make a mistake, please tell me, okay? Don't be watching for fun and then finally say, sir, it should have been that way. Then when A is 0, B is 1, that means this will be 1, C is 0, that means this is 1, that means there is a 1 here, output is a 1. Good. 0, 1, 1, this is going to be 0, because the 1 here is going to be translated to 0 here, and once it is 0, this is going to be 0, since it is a 0, the output is a 0. For the rest of the combination, I can blindly write, close my eyes and write as 1, because A is 1, it's an OR gate. So an OR gate input is, one of the inputs is 1, the output has to be 1. For all the 4 combinations of the last 4 combinations, for last 4 rows, output input is a 1, A is 1, so output has to be 1. So that means output F is, depending on the input variables A, B, C, can be defined as this, A, R, B and not C, and this is the output. So the whole thing is called the truth table. So I have the circuit, logical or Boolean logical representation, or the functional description, and truth table. What does it mean? There is some meaning. You can't just design a circuit arbitrarily, have 3 variables and make those variables change and then say output is 1 or output is false. Output is false when A is false, B is false, C is false. Output is false when A is false, B is false, and C is true, and so forth. And output is true when A is false, B is true, and C is false, and all you can say, go on saying it. It should have a meaning. It should have a meaning in terms of a control function, in a circuit function. For example, if you have an amplifier, I told you in the beginning, an analog device, analog circuits, you have an amplifier, I have a sound signal converted into an electrical signal by a transducer with the microphone, then it gets amplified, and the amplified signal is an electrical signal which is converted back into sound signal by a loudspeaker. Now, what is the function of the circuit? You can say it's an amplification function because my voice cannot be heard throughout the room. You have an amplifier to increase your. You can ask me to shout. The other alternative is to put an amplifier. Like that, what is the meaning of the circuit? That's what is the meaning. Everybody should have a meaning in life, right? This circuit has to exist with a meaning in his life. Otherwise, there's no point in existence. Can be anything. For example, it's a simple device. For example, this may be an event occurring. An event occurring. This could be an event occurring in a controller, bigger system, like a microprocessor. When does it get reset? For example, as a simple example, you get an error message. When does an error message come? On certain conditions being fulfilled. When error message comes. Those conditions are represented as variables, and when that combination of conditions occur, then it happens. Or it can be a chemical plant. There has to be a shutdown if there is a set of parameters taking certain values. So the chemical plant, or it could be a nuclear reactor. Then when you say nuclear reactor, it becomes more dramatic. It has to be shut off if certain things happen. And how do you monitor that? Somebody has to put a control circuit. And that control circuit will have variables called ABC, and that ABC variable will take these particular values. The value itself may not be important, but the combination of those values may be important. When the combination of those values ABC occur in this way, then you should automatically the circuit should trip so that you are saved. Some such thing. So like that, if you want to give a physical meaning to that, we can think of something like this. Supposing you want to know, let us take a simple everyday common example from everyday life. Supposing you want to go home. Let us say A is a Sunday. You want to go home. You usually go home on a Sunday. You normally go home on a Sunday. Let us say, or you go home on a Sunday. And you also want to go home whenever it's possible, other than Sunday also. For that, but you don't want to. Let us say you are one of those gem of a student who doesn't want to miss a class. Of course, you are not. That I know. But let us for a moment assume, make believe, assume that you are all very sincere students, you don't want to miss a single class of mine because you are so interested in my class. So I will say I will not go unless it's a holiday, right? So let us say B is a holiday. So I will go home if it is a Sunday or if it is a holiday. Then I could have A may be a Sunday, B may be a holiday other than Sunday. But I don't want to go on all holidays, but you are so sincere that even if it's a holiday, you don't want to go home if there is an assignment due next day, or there is a quiz next day, exam next day. So C may be the quiz. So if there is no quiz, and if it is a holiday, I will go home, or if it is Sunday, I will go home. This is some sort of a simple explanation, because in a real life situation I can explain this like this. Of course, in a chemical plant you can imagine a water level or a chemical level, fluid flow or temperature rising, or an aircraft landing system. Supposing he has the pilot sits in the cockpit and finds so many values, and some of the values are so critical for landing or taking off. If you do not reach those values, he doesn't want to take the plane. Or if he is flying, he wants to land immediately, certain combinations occur. These are done by monitoring these values, levels of transducers and various instruments. And when those things happen, you will land. Automatically the landing lights will go on, and whatever the landing procedure will take over. If it's an autopilot mode, it will go to autopilot mode so that the pilot will let the plane land by itself. So all those things. Or it could be a simple vending machine example. Supposing you want this and there is a cash. You want this, but it should have cash to put that, and there is the beverage you want may be available to you. So these are different conditions. Just because I want a coffee from a coffee machine does not mean I can't go and pray for coffee in front of a coffee machine. So I'll have to make sure that it works. That means I'll have to put a correct coin, and then supposing some machines give you change, some machines do not give you change. So I have to press the right button. So coffee must be available. There should be power. Coffee must be available. I should put the correct combination. Then a particular coffee or a beverage will be dispensed. So I can think of imagine many situations like that. You can do much more than that. You youngsters are supposed to be much more imaginative than us. So you can think of hundreds and hundreds of such situations where this type of control is required, which are implemented in terms of digital circuits and put in place so that finally the whole thing system works and you go without any worry on your plane, you sit down and then relax, and then the plane lands in the destination and you go home. But many things happen inside the circuit. So in this case I am going to then say F is go home, A is a Sunday, B is holiday, C no exam, C exam. So I go home on Sundays, and this is important, or on Sundays or on holidays when there is no exam. When you say no exam, it's the next day. I don't have to say all that. How can you have an exam on the holiday? Don't ask me all those questions. Okay. This is I'm trying to give you an example from your understand, but you can think of this as parameters that are critical in a chemical plant or an aircraft landing or a washing machine or an elevator. You don't want to get stuck in an elevator. That is worse than a plane crash. At least there you will die. Here you don't know what is going to happen to you, right? So these are the things you need to know. This is what. So now, given circuit, I should be able to analyze it, draw the truth table, and draw the inference, and finally say whether this is what you really wanted it. Is this what you really wanted? Is there any combination for which it gives an output when it is not required or should not be given? That's called a glitch. It's an error, hazard. Sometimes I get an output. I don't want, see, an error on the safe side is no problem. Suppose the plane does not take off. When you are supposed to take off, okay, you will curse the pilot or the airlines, but nothing is going to happen. But the other thing should not happen. When it is not supposed to be flying, it should not be flying. Right? So there should be no error. That means output, when analyze this, what is the purpose of analysis of a circuit? Make sure that outputs are required at the right time, given at the right time. No output is available when it is not supposed to be available. Or output is available at all the times it is supposed to be available. Both are important. So I should have a 0 exactly when I want 0 at the output. I want a 1 whenever I want 1 at the output. This is very important. I took an arbitrary example here. That is why I think like that. Now the question would be now, is it this circuit somebody gave me, I analyzed it and I said that I am trying to logically prove that this is something is going to do, it's a job. But is it the only way to do this? Is there a simpler way of doing it? How do you know whether the circuit is the simplest possible circuit to do the same operation? All I want is, now forget about holidays and going home and exams. A, B, C are 3 variables. I want an output high or true whenever A is present or B is present and C not present. Is it not? Is that what it is? Output should be true if A is true or if B is true and C not true. Is it the only circuit possible? You don't know. How did you get this circuit started? Because I gave it to you, you wrote the truth table and you analyzed it. So this may not be the best possible way to get the circuit. I don't know if it can be simplified. We'll have to see it. We have to look at the possibilities. But this circuit can be simplified and still gotten the same function. So we need tools, mathematical tools, to find out whether a given function, suppose the problem will be given to you like this, isn't it? This is the reverse thing I told you, but really it will be given like that. I would like to go home on a Sunday, whenever it's a Sunday, or on a holiday when there is no exam. Then you will program it, let us say. Just imagine. You program it in a computer and then it reminds you, tomorrow is a day off to go home. Or it's an alarm. In the case of an A, B, C being variables, when A is true or B is true and C not true, it's supposed to bring an alarm or light a bulb. Then I go and fix the circuit and then get this A, B, C and then power it up, connect power supplies, connect the lamp at the output which will glow, and then whenever the lamp glows I know that the system has been switched off or it is automatically switched off. Now having given this specification, how did you arrive at this? Because you simply took this and directly implemented it. I took the Boolean function, this is called a logical function or a Boolean function, two variable function, these digital functions, binary digital functions are called Boolean functions, because the whole thing was from mathematical background by a person known as Boole. Pardon? So because of that, so this Boolean algebra is called, it's a Boolean function we will call it, or sometimes they say logical function. And given this, I can directly interpret it in circuit, that's easy. But this is a very simple example of 2 gates, 3 gates in fact, one including inverter. So you won't mind if it is not very expensive, I can use 3 gates. But suppose I am thinking of a system or a subsystem with 1000 gates. Some complex example of a aircraft landing, I told you, aircraft landing is not going to be this simple, isn't it? Aircraft landing is going to be several parameters to be monitored and processed. It is not that wind pressure directly will be used as a transducer. Wind pressure will be coupled with some, speed, whatever is knots and all that, and altitude and temperature outside and everything will turn out and one equation will come. So there will be so many functions, so the complexity of the circuit will be very large. At that time it may be worthwhile to think whether it is directly given the equation should be implemented or see whether this equation can be simplified further and then implemented. When you simplify the equation further and implement it, you save on hardware. When you save on hardware, remember the mantra I told you. When you save on hardware, it increases the performance in terms of whatever it is, performance you are looking at, speed or whatever. Cost is lower, reliability is more because there will be fewer connections, interconnections. Power dissipation is lower, cost is less, size is small, everything. So if you remember that as the mantra, digital mantra, that high performance, low cost, small size, low power, if you want to add reliability, highly reliable. More and more components is going to be counterproductive in this, all of these factors. So you should have the same function performed with less and less of those components. There are 2 approaches. One approach is to go in for components which are not gate level, a slightly higher level of modules, performance wise. That we will see later. But before we go to that, in a gate sense itself, only using the AND or invert or NAND NOR, that type of gate level implementation, there are lots of things you can do to improve or to reduce the complexity of the circuit. Given function need not be directly mapped onto a circuit. Directly given a Boolean function or a word description, this is a word description, this is the Boolean description. Given a Boolean function or a word description, it's not necessary to jump to the nearest gate and then start connecting it. You always examine it and see whether it can be simplified further. There are tools available for it to make it systematically. One such tool is called Boolean algebra. So I told you the whole thing a digital binary. Binary variables, things with binary variable, binary functions, using logical operations like AND or invert. Whole thing is the name is named after Boolean. Boole is the name of the mathematician. So Boolean function, Boolean variable. Similarly, the algebra or the mathematics that is used to simplify the Boolean function to a equivalent function which is performance wise identical but uses less hardware, less number of gates. That tool is called Boolean algebra. So we have to learn Boolean algebra. I am not going to teach that. It is not a very, first of all, it is not a great thing. It is a very simple set of rules. It is only binary variables. A variable can only take two values, 0 or 1, true or false. And even the Boolean algebra sometimes is not very, see something, whenever there is a mathematics involved, you have to apply it properly. So you will never know you have applied it the right way. You always have a doubt at the end of the day after applying a Boolean algebra to a given mathematical function, a Boolean function. You got a simplified function which is identical to the first function. You are not sure whether this is the simplest function or can it be simplified further. Who is going to tell you that? I give you a problem in the exam, given a Boolean function, simplify it to as few variables as possible, using as few operators as possible. There are two things you have to be worried about. One is the number of variables, the other is the number of operations. So you will have to have as few operators as possible, operations as possible, and as few variables as possible. So I give you a thing and then reduce it to the minimum possible number of operations, minimum number of variables. I gave a function with 8 operations and 9 variables, and somebody got 3 variables and 2 operations, somebody got 5 variables, 4 operations. We don't know who is right, who is wrong, which is the best fit. So there is another thing. This is the algebraic method, the other is called map method. From here we will go to map method, where you can do a graphical simplification of getting the simplest possible solution for a given Boolean function. These two things we will see. Boolean algebra we will see quickly. I am not going to spend a lot of time on Boolean algebra for many reasons. One is that, as I said, the map method gives you a much better, easier way of getting the same goal. If you can get something easier and more reliably, map function always gives you the best possible result, the minimum possible solution in terms of the number of gates and number of variables. Number of variables and number of operations, I get the map method always reliably the lowest. When that is the case, why should I go to another method which is not so reliable unless I apply it carefully? Unless I exhaust all possibilities, I am not sure I am going to go. Second thing is gate saving is no more a big issue today, because gate saving was supposed to be very, very important. The early days of all this hardware being developed, and it's all very expensive to go through, so instead of something like inflation in terms of electronics, when probably when you talk about earlier days, you want to save a rupee, today you want to save 100 rupees, 100 is not worth saving anything less than 100 rupees. You keep the change, you can say. Of course, all of you, especially who are spending your parents' money, you will be even more generous. What I am trying to say is, the gates are so, the technology has advanced so much, in a small area of silicon they can put thousands and millions, even millions of gates. So what is the need for saving 1,000 of those million gates? 1,000 less, if you have 1 million rupees, if I ask you 1,000 rupees, of course, I don't know you will give me, but I am just saying, but you won't mind it, no? At least somebody to whom you want to give, you won't mind giving, maybe not to me, but to somebody. But if you have only 2,000 rupees, when somebody asks 1,000 rupees, you will think twice. So the saving of the gate came at that time concept. Today, gate saving is not a big issue, because now we go for system level and subsystem level, where functionally we are interested in functional minimization. functional efficiency, all those parameters I told you again repeat, power, reliability, cost, etc. When that is the issue, we will not worry about having one extra AND gate there and one extra OR gate there. Because of these two reasons, but you should know, as having gone through this course for completeness sake, I will quickly introduce you to Boolean algebra, maybe in half a class or so, and we will spend a little more time on map method because it is a systematic graphical method of simplifying a given Boolean function to get the minimum possible hardware solution for a given function or a given description of the problem. We will see that in the next few classes, subsequent classes, but before that I want to give you some definitions today before finishing it off. We said this is the truth table of the system. The truth table has, as I said, first we already defined truth table. It has all the input combinations and the corresponding outputs. I will not write the definitions here. Truth table will have all the inputs and the corresponding outputs, all the possible input combinations and the corresponding outputs. And the number of entries in the truth table, we know that is 2 power n, where n is the number of inputs, right? So number of rows, 2 power n rows, where n is the number of inputs. Now each of these is called a min term. For example, you can say now, instead of saying this f is true if a is true or when b is true and c not true, that is one way of saying, if I did not know this function, if you did not give me this word description of the problem, or if you did not give the Boolean algebra, or if you did not even give me this circuit, and if you only gave me this truth table, I will read this as f is true when a is false, b is true, c is false. F is true when a is true, b is false, c is false, like that I will start reading, is it not? So you can write this f as, from a truth table directly as, in this case, what? A bar, quickly tell me, a bar, b, c bar, or a, b bar, c bar, a, b bar, c, a, b, c bar, a, b, c, right? In each of these outputs, this is called the minimum, this is called the sum of products expression, SOP. It looks like a sum plus, even though it is not a plus, it is an OR operation. Since we are used to arithmetic, and each one is an AND operation, A bar and, but this looks like a product. No, it looks like a times B times C. So this is called the sum of products. The output can be expressed as sum of products directly from the truth table. Of course, it can be simplified later on, I told you, by either graphical method or Boolean algebra method. So this is called, when I say somebody says sum of products, it should be like this, and this is particularly called canonical sum of product. Canonical sum of products. That means in a canonical sum of product, each product term will have all the variables A, B, C, either in the true form or the complement form. That means if from a truth table, if you read the sum of product, it will be a canonical sum of product. When you simplify the canonical sum of product, you will get a minimum sum of products. So you will have to first write the truth table, get the canonical sum of products, and then simplify it either Boolean algebra way or map methods, and then get the minimum sum of products. And each of these term is called a min term. A b bar c bar, a bar b bar c, etc. are called min terms. So these are the definitions I want to tell you. This is the truth table. This is each, the expressed product is expressed, the function is expressed as a sum of products. Normally we have variables and operation and all this with OR operations. That is why it is called sum of products. But if in each of these terms, if all the variables are present either in the true form or the complement form, it is called a canonical sum of products. That is what you can directly obtain from the truth table. and simplify it to get the minimum sum of product, or it need not be minimum. You can simplify to get a sum of product. If you simplify it long enough, you will get the minimum sum of product, and that can be implemented using hardware. So I want to know this truth table. I want to know what is product term, sum of products, what is meant by a product term, what is by a min term. Min term is what you have in the truth table directly, and the term canonical refers to the output read directly from the truth table. So with these definitions, next class I will briefly give you the overview of Boolean algebra very quickly, and then we will go on to the map method of reducing the given Boolean functions so that we can get the minimum sum of products from which you can get the most efficient hardware for a given function. Okay.